In this video, we are going to discuss about hard soft acid base theory. Simply HSAB. H for hard, S for soft, A for acids, B for bases. There are so many concepts to explain the acidity and basicity of compounds. First one, it was Arrhenius concept. According to this, species which give H plus will give are known as acids, and the species which give OH minus is known as bases. This concept is applicable for HCl or H2SO4, HNO3, or even carboxylic acids. All these compounds can release H plus when it dissolved in water. This OH minus can go for sodium hydroxide, KOH, calcium hydroxide. All these compounds, when it dissolve, they will give OH minus. But the problem is, what about this compound, K2CO3? There is no OH in the molecule. Similarly, ammonia. It will not dissociate to give OH minus. So it was not able to explain the basicity of this. Similarly, acidity of BF3 was not able to explain by this one. The second one is Bronsted acid base concept. It is somewhat more general than Arrhenius. According to Bronsted, acid is a substance which donates H plus. So similar to this. So it gives H plus. It need not dissociate completely. If it gives H plus, then that is called acid. So here that is dissociation. But here if it gives H plus, then we call it acid. Base which takes H plus. For example, take K2CO3, and if you add H plus, it will become KHCO3. So it has taken this H plus. Even though it is not giving OH minus, it can take H plus. So this is known as base. If you go for acid, Bronsted acid and Arrhenius will be almost same. But when you go for basicity or basic compounds, that is somewhat different. Which takes H plus is known as bases. Third one, Lewis acid and bases. This concept, it is based on donation of lone pair electron or acceptance of lone pair of electron. For example, if you go for water, it has lone pair of electron. It can be donated to another molecule to form a coordination bond like this. Now this is known as base, which donates the lone pair of electron is known as base, which accepts the lone pair of electron, it is acid. The very well known Lewis acid is BF3. Since fluorine has more electronegativity compared to boron, in BF3 the electron density on fluorine is very less. So there is more del plus. So if you add even ether, I go for diethyl ether, the lone pair of electron will attack this. So it will exist as BF3 etherate. So there will be a coordination bond between this oxygen and boron. So that is known as Lewis acid. There are so many other Lewis acids like AlCl3, SnCl4, like titanium salt. So there are so many such Lewis acids. Generally, the transition metals, almost all the transition metals, when it is attached with electron withdrawing group, they act as Lewis acid. For example, scandium triflate, titanium tetrachloride, titanium tetraisopropoxide, ferric chloride, cobalt chloride, nickel chloride. All these compounds, they can act as Lewis acid. Even copper triflate, maybe 2 or 1. Zinc triflate. I have attached some electron withdrawing group like Cl, Tf to metal. The electron withdrawing group pulls the electron density from zinc, so there is more del plus on metal, and the base, Lewis base, donates a lone pair of electron to metal. But in this video, we are more focused on HSAB. In order to explain that, I go for this compound. This is nothing but Na2SO4, sodium sulfate. So this is the structure for sodium sulfate. You may be familiar with this structure, but these are the bonds present in the sodium sulfate molecule. Go for another molecule. Calcium carbonate. Calcium, it is 2 plus, carbonate 2 minus. Or I go for silicon dioxide. Silicon dioxide, you may know the formula is SiO2, but it is not a monomer. It is basically a polymeric silicon dioxide. Further, it will be attached with silicon and it will be 3-dimensional structure. So that is why it is very hard. This SiO2, in this, silicon is attached with oxygen and the earth crust is made up of this. Similarly, if you go for aluminium oxide, Al2O3, in this, aluminium is bonded with oxygen. Now the question is, why these metals prefer to bond with oxygen? Now I go for another set of compounds. They are basically ore. It's nothing but zinc. Zinc is available as zinc sulfide. We call them as zinc blend. So zinc has more affinity towards sulfur. Similarly, if you go for mercury, mercury has more affinity for sulfur. That's why they are called as mercaptans. Sulfur compounds, they are known as mercaptans because it has more affinity towards mercury. Similarly, if you go for copper pyrite, so basically that is nothing but copper sulfide compounds. Now you compare these two sets of compounds. The first one, the metals, sodium, calcium, silicon, aluminium, it is bonded with oxygen. But in this case, the metal has bonded with sulfur. What is the reason? Why these metals has preference for oxygen while these metals has preference for sulfur? In order to explain this, hard soft acid base theory was proposed. According to this, hard acid prefers to bind with hard bases. Similarly, soft acids prefers to bind with soft bases. So it is very simple principle, anybody can remember. But the problem is, what are hard acids and what are soft acids? what are hard bases and what are soft bases. If you go through the book, it is given. But it is not possible to memorize all those things. If you go for the book, it will be somewhat difficult. I have a simple method to remember the hard, soft, acid, base concept. Here I have given the periodic table. The first one, these are bases. So here we have carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine. So arsenic, selenium, bromine, antimony, tellurium, iodine. So these acts as bases. On the other hand, if you go for the remaining compounds, all these compounds, they act as acids. So bases are only a few. So you can easily remember that. Further, the bases, they classify this region, that is oxygen, fluorine and chlorine, as hard bases. This region, they are soft bases. So phosphorus, arsenic, antimony, selenium, tellurium, bromine and iodine, they are soft bases. Nitrogen, sulfur and chlorine, these three compounds, they are known as intermediate or borderline bases. Now it will be somewhat easy for you to remember. If you try to memorize what are the hard bases and hard acids, it will be difficult. Instead of that, if you go for this periodic table, it will be somewhat easy. Now let's go to the acids. Almost all the metals comes under that. So all these are metals, but these are non-metals or metalloids or non-metals. But here all the metals act as acids. In this region and this region, together they are hard acids. So hard acids are more. Soft acids, only a few. Around 11 metals, they are soft acids. The soft acids are only in transition metals. You can see here ruthenium, rhodium, palladium, silver, cadmium, osmium, iridium, platinum, gold and mercury. So these are soft acids. So easily you can remember. Just the compounds which are below iron to zinc, they are known as soft acids. If you are able to remember this, then the metals which are surrounding that, they are known as intermediate or borderline. When you go for zinc, it prefers to bind with this. Copper, it can form bond with ammonia as well as Cl. So you can try to analyze the compounds based on that. If you go for these compounds, lithium, sodium, potassium, rubidium, cesium, francium and alkaline earth metals, they are always hard acids. They prefer to make bond with oxygen and fluorine and with chlorine. You cannot find compounds in which a bond is found between alkali metals and ammonia or sulfur or with these atoms. It is basically very simple concept if you go through the periodic table. Instead of that, if you try to memorize what are the ions are present, what are the metals are present, then it will be very difficult.